Hi, and welcome to Software Design and Development, Implementation, Lesson 7 and Lesson 8, Error Checking. Here are the dot points covered. Please pause if you'd like to read them. And as always, remember to take notes. So, with errors, there are three types of errors. We have syntax errors, we have logic errors, and we have runtime errors. Syntax errors occur when the rules of the language have not been followed. The program will not run as the program does not know exactly what it needs to do. Examples include listed here, things like ifs without end ifs, whiles without end whiles, typos, leaving special characters, etc. It depends on the programming language what the syntax errors might be, but basically when you are going against the rules of the language, you will have a syntax error, and the program will, it won't compile, it won't interpret, it just won't run. It'll flash up the line that has the issue, and it will wait for you to fix it. Logic errors are the hardest errors to find, and they're when the program does not do what you want it to do. Okay, it will run but will output an incorrect result, and they are 100% the result of programmer error. They aren't a result of the computer not doing the right thing. They are a result of you not writing the code in a way that solves your problem correctly. So things would include incorrect counters and loops, misspelling of variables, so using one variable instead of another, using a while loop instead of a repeat loop, or vice versa, because they have issues. A while loop does not have to run, whereas a repeat loop will run at least once, so that could cause an issue, and anything else. So yeah, if you're using the wrong code to get your job done, basically. Runtime errors occur when something occurs during the running of the program that causes it to crash. Okay, so you won't find these programs until you actually run the error. You won't find these errors, sorry, unless you actually run the program. That makes sense. And there's a variety of examples of these. One's arithmetic overflow, and that's when a variable tries to store a value that is too big to fit in it. Example, Visual Basic, an integer uses 32 bits to store a value, and so that gives you a possible, a number of possible values from minus 2 billion, minus 2 billion 147 and something, through to positive 2 billion 147 and something. Anything above for positive and below for negative, these values will cause an overflow. As the program doesn't know what values are going to be stored in it at the time of running, they'll only crash when you try to stick the value into the variable during runtime. Division by zero is another one. If you try to divide by zero in maths, this is undefined. It's impossible. It's not infinity. It is actually impossible to do. Okay, you can Google it yourself. I'm not going to cover it here. But basically, the computer will crash because it cannot do it. And the other thing is, as it's a runtime error, the computer doesn't know you're going to try to divide by zero until it actually runs. The most obvious would be something like this: total equals sum over zero. That will obviously crash. But can also occur if you've got something like this, where count might go to zero at some point. So you need to make sure that if you're dividing and you're dividing by a variable, that it can never equal zero. Okay, and then accessing inappropriate memory locations. So this can occur, for instance, if you have an array that's defined from 1 to 10 and you try to access index 11, okay, or a negative index. The computer doesn't know what that is because the memory location doesn't exist, and it will crash when it tries to access it. And there's a number of ways you can detect and correct these errors, and they're listed here. We have flags, and flags are a simple Boolean variable that can be turned on when something occurs in your program. They're not just an error checking process. They can be used as normal variables to confirm if a process is run or to flag something for something else. But when we use them as errors, error checking things, we look for processes that have run or some other value we need to check. And we just set it, usually they stay false, and we set it to true when it happens. Okay, and they're a way that we can easily track what's happening in our program when it's running. The most important one would be the methodical approach to the isolation of logic errors. And so moving through your code methodically, checking code line by line, you can avoid many logic errors. Okay, we combine this with single line stepping, which is a error checking technique we'll cover next lesson. Use of debugging output statements. A debugging output statement is similar to a flag, except we actually output the result to a screen. So we can output a variable to a screen or a message or whatever. We can track variables, so you might print the status of the count in a loop to count how many times it runs. You might print the status of a total in a loop to see that it's adding the total up correctly. You could do any number of things. I find this to be one of the most useful one of the most useful error checking techniques, because you can actually see what's happening as the program is running. Otherwise, the program just runs too fast and you can't track the variables. This is a really, really easy way to do that after the program's run. You can step through and it's kind of like a desk check. You can see what's happening. Peer checking involves getting a peer to check your code. So you get a trusted person to sit next to you and they will check your code with you, and they'll oftentimes find errors that you've missed. We become very attached to our code. We think we're perfect. We assume that it's all good. And we miss sometimes very obvious things because we're overlooking them and looking for small things. So a peer can come in, not know what the code is, and really easily find those things. Desk checking is really important as well. So we don't just desk check when we write our algorithms, we also desk check when we've written our code. And it's a way to confirm through pencil and paper what our program is doing. The key here is to make sure that we desk check the code exactly as written, and we don't check what we think it is meant to do. So I've written the point here, check what it does, not what it is meant to do. And oftentimes you won't need to finish the desk check to find where the error is. You can just desk check to the point where you find the error and suddenly you have an aha moment and you're like, yep, I know what that problem is. Structured walkthrough. These are really important. Okay, so structured walkthrough is where the programmer of the code leads a meeting with a group to find bugs. Okay, I've got this guy called Edward Jordan who wrote a book in '79 about structured walkthroughs, and it was pretty detailed on how these are. There's a set of roles, and they all need to be covered, but they don't need to be covered by separate people. So you might find one person assumes a number of roles in this process. Firstly, you've got the presenter who describes the specifications, the code, the reasons things were done. And so he basically says, here's my code, I did this because of XYZ reasons, so that the people have an idea of what's meant to be happening and why. You have the coordinator, who's like the chairperson of the meeting. He keeps the meeting on track and makes sure that people don't devolve into arguments. The secretary's job is to take notes on the meeting. Okay, really important, so we actually know what happened in the meeting so we can go back and fix the issues raised after the meeting. We've got the maintenance oracle, or the QA inspector, which makes sure the code is readable and maintains the standards set up by the company. We have the standards bearer to make sure the coding standards the team agreed on beforehand are maintained. So the code needs to follow a set standard, a set structure. If the code does not follow that structure, the meeting's pointless because everyone will be focusing on that and won't be focusing on the other issues. If it is in the same structure, then you can ignore that and you can very easily see the problems instead of focusing on the differences in the structure of the code. You have a user representative which is present at certain walkthroughs to ensure the customer who wants an orange doesn't get a brick. So basically making sure the customer, what they asked for is what they're going to get. And you obviously have other programmers who will be the experts and tell the presenter where the issues are in the code. And the other important point we have is a comparison of actual with expected output, where we look at what the code is actually spitting out at the end and what we actually want it to spit out at the end. If there's an issue there, we can see that we actually have an issue. Oftentimes we might find that the actual and expected outputs are the same, but there are still errors. So we need to ensure that we have multiple sets of test data to find those.